course, we can sort of consider the fact that the mass and the weight are somewhat synonymous with one another. They're slightly different because of gravity. Okay, and so what's a little bit more interesting than that is the fact that some of these elements will have isotopes. Isotope means the same. And so an element is kind of a mixture, if you will, like carbon is a mixture of carbon-12, carbon-13, carbon-14. You're like, wait a minute. What is that? Well, all carbon has the same atomic number, which is 6 protons. Nothing in the universe has 6 protons but carbon. But apparently there can be different masses. And if there's different masses, that means there must be varying number of neutrons. And so different variations of carbons are called isotopes. And there's many elements that have isotopes. Yeah, like what's the point of it? Well, some isotopes are useful in different disciplines. They can be used in chemistry, they can be used in biology, they can be used in medicine. And one of the things about it is that some of these isotopes are not very stable, meaning that they can decay and they emit particles. Now, that's a whole big discussion. They can emit electrons or beta particles, or they can release alpha particles, or helium nuclei. And basically, when they decay, they can turn into a different element. And so they can, as a result, break down over a period of time. And you're like, well, gee, how fast is this? In some instances, radioactive isotopes can break down rather quickly. In some examples, very, very, very slowly. So slowly that perhaps it's more realistic to consider how long does it take for half of it to break down. It's sometimes called a half-life. And carbon is an example of that. Carbon-14 is radioactive, and so when half of it, so in other words, say I had 2 grams of carbon-14, it will eventually break down to nitrogen-14. And as a result of that, when half of it, so 1 gram remaining, when half of it breaks down, it takes 5,730 years. And so that can be kind of useful when you're dating things in the past. Like, for example, the study of paleontology, the study of fossils, you can sort of look at bones and scrape out some of the tissue. Now, why is carbon isotopes useful? Because living things contain carbon. Like, for example, like for us, we'll either eat carbon by eating an animal or we'll eat a plant, and the plant ultimately gets it from the atmosphere. And so all living things have the same ratio of carbon-12 to carbon-14 because it comes from the atmosphere. So as it turns out, if you're no longer breathing or eating, that means that the carbon-14 will begin to decay and carbon-12 will remain the same. So you can look at those ratios to determine the age of a fossil. So it's kind of useful. This is T-Rex. And so some shorter half-lives are useful when tracing medicines. Like you can see here in this PET scan, looking at what looks to be a pig here, you can use different radioactive isotopes and incorporate them into different compounds that you're maybe considering as medical treatments of pharmaceuticals. And so you can sort of look at this and see where they're going in the body. It can be rather useful, radioactive isotopes. In a separate video, I can talk about how one of the great examples, one of my favorite examples of how radioactive isotopes were used was one of the Nobel Prize-winning scientists from the University of California, Berkeley, Melvin Calvin. He used radioactive 14 in carbon dioxide, and he pumped that into this container of algae, and he was trying to determine how plants, although algae is not technically a plant, but how plants use carbon dioxide to produce glucose. And he knew it wasn't a one-step chemical reaction, that it was some kind of pathway. And so he used radioactive carbon-14, and he saw, through using X-rays, he saw compounds containing that material, and then he used different amounts of time as a measure of the pathway. And so he was able to determine that the pathway to producing glucose was cyclical, and he was able to determine the sequence of the reactions. I mean, absolutely incredible, Nobel Prize. So one more thing that I want to say about an atom is that, there's a lot of analogies, but if the nucleus was a golf ball, like where are the electrons? We mentioned they're flying around at the speed of light. 186,000 miles per second. Well, they would be about a kilometer away from that golf ball, so that's approximately a mile. So it's a lot of space, hard to even conceive. If you're following this, you must understand that we're mostly empty space as a result of that, because there's so many atoms that we have. So it's kind of mind-blowing a little bit. So atoms are mostly empty space. But yet, the nuclei, therefore, don't come very close to one another. It's the electrons that are the ones that are involved in interaction. And so our focus in the class is going to be on the subatomic particle of an electron, because those are the ones that are interacting. And so what we say about an electron? Well, electrons are negatively charged. They're an incredibly small mass. And they're able to possess energy. And so what does this mean? Well, energy is, the definition of energy is the ability to do work. So there's 2 types of energy. There's the energy of potential, which is the energy of position, or there's the energy of motion, which is kinetic energy. And so, like for example, potential energy is if you put water up in a water tower, it has the potential to do work when it's released, or if you store it behind a dam, then you release it, it has the ability to move and produce electricity by pushing turbines and generating like copper around a magnet and making electricity. So potential and kinetic energy. So these electrons, what happens is the further they are away from the nucleus, so like steps of a ladder, the more potential energy they have. Like it's a measure of distance. So the further the electrons are from the nucleus, the more potential energy they have. And so as it turns out, these electrons, though they're moving incredibly quickly, the distance from the nucleus for some electrons are discrete, and so there are these fixed distances, and we sometimes refer to them as energy shells or electron shells. This might be familiar with your background in chemistry. So the very first shell has the least amount